In the last video, we talked about formal specification and tracing through code. In this video, we'll talk about how to verify your code in general. As the coffee blogger says, we're going to focus on verification in this video. Here is the operation we want to verify, transfer top. Previously, we showed this operation with an informal specification and traced through the code for specific inputs. This time, we want to verify that this code works for all possible inputs. The requires clause states that the first stack cannot be empty. The ensures clause states that the first stack loses its top element and the second stack gains the first stack's top element. Now let's look at how to talk about the input and expected output symbolically. In a normal computer program with state changes, the values of the variables change from state to state. To guarantee that we know which value we're talking about when we mention a variable symbolically, we're going to index the variables with the state that they are in. For example, S1 will represent the value of S in state 1, and S3 will represent the value of S in state 3. In state 1, what do we know about the values of variables S and T? Well, we know that S and T are both stack objects. But if you look at the requires clause, you also realize that S cannot be empty. Therefore, under input, we're going to put that S1 is not the empty sequence. For our expected output, it seems like we would want to put what's in the post condition. However, we have to use correct indexes for the variables. There are two kinds of variables in our post condition. Variables with a hash indicating incoming values, and variables without a hash indicating outgoing values. I won't ask you to pause the video for this, but if I give you 10 seconds, can you tell me what variables without a hash should be indexed with and what variables with a hash should be indexed with? 10 seconds starting from now. Ready? Variables with a hash are incoming values. They should be indexed with the first state possible. In this case, state 1. Variables without a hash are outgoing values. They should be indexed with the last state, in this case, state 3. So the expected output is simply S3 equals all but first of S1, and T3 equals the sequence containing first of S1 concatenated with T1. This is a symbolic reasoning table. In addition to state and facts, like the tracing table, this table also has a column for obligations. Obligations are assertions that will eventually need to be proved by using the facts. More complicated symbolic reasoning tables also have a column for the path condition that's used when your code has conditions such as those found in if statements and while loops. From the last slide, we have already filled in two cells in this table, the first facts and the final obligations. The first facts always come from the precondition of the operation we're trying to prove correct, and the final obligations always come from the postcondition of the operation we're trying to prove correct. In this case, that operation is transfer top. For all the other facts and obligations, the order is reversed. For all obligations except the last, the obligations come from the precondition of the operation that follows it. Likewise, for all facts except the first, the facts come from the postcondition of the operation that precedes it. Why is it flipped like this? Well, the first facts and the last obligations are special. We want to show something about the method we are implementing, transfer top. However, for all of the other statements here in this reasoning table, we're not implementing them. We're using them. So we have an obligation to obey their preconditions. If we do, we're guaranteed that the post conditions will hold. Let's look at the first statement, which involves a call to the pop method. First, we'll bring up the specification for the pop method. Since we are calling the pop method, we have an obligation to prove that the requires clause is true. In this case, since we're calling the pop method on variable s, we have an obligation to prove that s is not empty. We write this as an obligation in state 1 before the call to pop. You might think that the obligation in state 1 would be easy to prove, since we have a fact in state 1 that says exactly the same thing. If you thought that, then I have good news for you. You're absolutely right. Okay, provided we can prove that obligation, we're guaranteed that the post condition will hold after the call. In this case, that means that the new value of s in state 2 is going to be a sequence just like s in state 1, but without the first element. The first element will be returned and stored in the temp variable. So the facts in state 2 are going to look like this. Note that since t was not involved in the statement, its value did not change. This is reflected in the assertion that t2 equals t1. Okay, that's all for the pop operation. Now let's look at the push operation. The push operation has no precondition, so there's no obligation in state 2. The facts in state 3 are acquired similarly to the facts in state 2 from the ensures clause of the previous statement. This corresponds to t. Element corresponds to temp. The outgoing values are going to be indexed with state 3, and the incoming or hash values are going to be indexed with state 2. And s does not change. Okay, now let's ask the same question we asked after we completed the tracing table. What have we proved? Please pause the video and try to answer this question as best you can. Ready? And the answer is nothing, at least not yet. What we want to prove, what we would like to prove, is that the code is correct with respect to its specified behavior. And we can say that we've proved that as long as we can discharge all of the obligations. Discharge is another word for prove in this context. We've already seen that obligation 1 was trivial to prove, and there was no obligation 2, so we just have to worry about obligation 3. You might think that the final obligation would usually be the most difficult to prove, and most of the time that's true. So let's look at just one portion of the final obligation. I've written the facts from the symbolic reasoning table in the rectangle at the top of this slide. The facts from state 1 are on the left, the facts from state 2 are in the middle, and the facts from state 3 are on the right. We want to prove part of obligation 3, that T3 equals the sequence containing the first element of S1 concatenated with T1. Here's one way to do that. Notice that one of the facts in fact 3 says that T3 equals the sequence containing temp2 concatenated with T2. Let's use that fact to replace T3. Now we have a singleton sequence plus some value of t on both sides of the equation. Well, guess what? In fact 2, we have the fact that T2 equals T1. So let's replace T2 by T1. Now, just using regular mathematics on sequences, we know that this is the same as saying that the sequence containing temp2 equals the sequence containing the first element of S1. In fact, since these are singleton sequences, their first and only elements would have to be equal. So we end up with this. Temp2 equals the first element of S1. Lo and behold, this is the last fact in fact 2. So we just proved this part of our obligation. And that's it for this video on verification. In the next video, we'll see what the future holds for formal verification systems.